Hey, welcome. When we describe the world, some things are pretty simple, right? Like speed or mass. You just need a single number. But what about something like the push of the wind or the pull of gravity? For that, a number just isn't enough. You need something more. You need a vector. So let's demystify this thing, shall we?
Okay, let's get right to it. Here is the absolute core difference. On one side, you have a scalar. Think of it like speed. It just tells you how much. Your car is going 100 kilometers per hour. That's it. But on the other side, you have a vector, like velocity. It tells you how much and which way. Your car is going 100 kilometers per hour north. That little piece of directional information, that's the secret sauce. That's what makes a vector so incredibly useful.
All right, let's break this thing down. Section 1, the anatomy of a vector. We're going to look at it in two ways. First, what it looks like as a simple picture, and then how we talk about it using numbers.
So at its heart, a vector has just two key ingredients. That's it. First, it has magnitude, which is really just a fancy word for its size or its length. And second, it has direction, which, is exactly what it sounds like. You put those two things together, magnitude and direction, and congratulations, you've got yourself a vector.
Honestly, the absolute easiest way to think about a vector is to just picture an arrow. It really is that simple. The length of that arrow, that's its magnitude. And whichever way the arrowhead is pointing, that's its direction. The entire concept right there in one simple image.
Now here is a really important idea, and it might feel a little strange at first. A vector doesn't care where it is in space. As long as two arrows have the exact same length and point in the exact same direction, they are considered the exact same vector. It doesn't matter if you draw one in New York and one in Tokyo. If they're the same length and point the same way, they're identical.
Okay, so drawing arrows is great for getting the idea, but to do any real math, we need numbers. And we do that using components, which we write inside these little pointy brackets. So if you see the vector 3, 4, you can just think of it as a set of instructions. It says, from wherever you start, move 3 units over to the right, and then 4 units straight up.
So now we know what a vector is. But their real magic isn't what they are, it's what they can do. The real power comes when you start playing with them, combining them, stretching them. To see how that works, let's jump into a little story.
So picture this. You're out at a huge state park, and your friend has gotten lost. You've got a couple of different clues about where they might be. Well, vectors are the perfect tool to take those separate pieces of information and figure out exactly where you need to go.
Okay, so hike number 1. Starting from your car, you head 3 kilometers east and then 4 kilometers north. We can represent that whole trip with a single vector. Let's call it vector U, which is just our old friend 3, 4. So you get to that spot, but no friend. You call a park ranger, and they give you a new heading. From your current spot, you need to go 1 kilometer west, which we can think of as -1 on the x-axis, and then another 4 kilometers north. Let's call this second journey vector V, and its components are -1, 4.
So how do we combine these two hikes to find the final spot? Well, visually, it's super intuitive. You just draw the first vector, and then right where it ends, you start drawing the second vector. We call this placing them tip to tail. The total journey, a new vector we'll call W, is simply the arrow that connects your original starting point all the way to your final destination.
And what's really, really cool is that the math is even easier than the drawing. You literally just add the matching components together. For the horizontal part, 3 plus -1 gives us 2. For the vertical part, 4 plus 4 gives us 8. So the final vector that gets you from your car to your friend is 2, 8. It's as simple as that.
Okay, let's tweak the scenario a bit. What if the ranger had said your friend was actually 3 times as far away, but along that very first path you took? Well, you don't need a new direction, you just need to stretch your original vector. We do that by multiplying it by a scalar, in this case, the number 3. You just multiply each component by 3, and your new destination vector becomes 9, 12.
All right, we've spent a lot of time on a vector's direction. So now let's dig into its other half, its magnitude. How do we actually calculate, with precision, the length of one of these arrows? To figure this out, let's bring back our favorite vector, 3, 4. We already know what those components mean, right? It's a set of instructions. Go 3 units over and 4 units up.
So the question is, how long is the arrow itself, the actual path you traveled? Well, if you sketch it out, you'll probably notice something familiar. The 3 units over and the 4 units up parts actually form the 2 legs of a right triangle, and the vector itself, that's the hypotenuse. And if you can dust off that old geometry knowledge, you'll remember that a right triangle with sides of 3 and 4 always has a hypotenuse of 5. And that's it. That's our answer. The length, the magnitude of the vector 3, 4 is simply 5.
So that little aha moment we just had, well, there's a name for it, the Pythagorean theorem. And that's exactly what gives us the formula for any vector's magnitude. You just square the first component, square the second component, add them together, and take the square root. And that symbol, those double bars around the v, that's just the official way we write the magnitude of v.
Now, here's a cool idea. What if we only cared about a vector's direction, and we wanted to completely ignore its length? For that, we have a special tool called a unit vector. It's just a vector that has a magnitude of exactly 1. Think of it as pure, distilled direction.
And making one is incredibly easy. It's a simple two-step recipe. First, you calculate your vector's current magnitude. We just learned how to do that. Then, you simply divide each of the vector's components by that number. What you're left with is a brand new vector that points in the exact same direction, but now its length is perfectly scaled down to 1.
So we've gone through the what and the how of vectors, but that leaves the most important question. Why? Why does any of this matter? Let's zoom out and look at the big picture, because this is where it all comes together.
Okay, so let's do a super quick recap of the tools we've just built. We now know that vectors are all about magnitude and direction. We know we can add them together by putting them tip to tail. We can stretch and shrink them by multiplying by a number. We can find their exact length using a bit of geometry, and we can even strip them down to their pure direction using unit vectors.
And I want to be clear, this toolkit is so much more than a neat math trick. This is literally the language of science. It's how physicists describe the force of gravity pulling you down in your chair right now. It's how engineers calculate the exact velocity a spaceship needs to reach orbit. It's even how you figure out the twisting force or torque needed to tighten a bolt. It's everywhere. So from now on, when you feel the wind on your face or you watch a ball arc through the air, I want you to remember the invisible vectors that are hard at work. You now have a new lens to see the world. So my final question for you is this. Now that you know how to look for them, what forces will you start to see?